You get it? Okay. I will begin. Dear Father, we thank you for this day. I thank you for the students and for the break. Just help us to just get back in the swing of it and to accomplish much today, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right. So today I am talking about group actions again. And this time from a slightly different perspective, although not terribly different. And so we're hopefully going to dig a little bit deeper into essentially an oh man, well this is just the worst. Did I leave my notebook over there? Is my notebook back there or something? Well, this is most unfortunate. Huh. Well, oh, yeah, look at that. All right, well, I guess I left my notes downstairs. That's not the end of the world. I will just... I would resist the urge to start projecting at the start. Come on. So sorry for the delay here. We are in lecture 17, which is on conjugacy in the class equation. This is actually the start of a longer discussion, which we won't have in here. This naturally leads to what are called the Silo-P theorems, or Silo. I really don't know which it is. But this is lecture 17. Which is mostly going to be about conjugacy and the class equation. All right, so to start with, I want to point out to you that, well, actually, let's take a step back and just look at an example. This example has not too much to do, I suppose, with everything else we're doing in here. We defined how to look at a subgroup of permutations, right? If I had H was a subgroup of, say, Sn, it can act on, n sub n, the numbers 1 through n. How do we do it? We just said sigma acting on x was equal to sigma of x, and that was one of my first examples, right? So I think it's actually instructive to look at this for a specific subgroup and maybe a specific choice of n. All right, so let's narrow the focus. Let's consider, how about n equals to 13, and let's let H be the subgroup generated by sigma, and I don't know, I need a particular cycle that's at least a little bit interesting. How about this? Sigma is equal to 1, 3, 5, 7, 2, 4, 6, and I don't know, how about 9 and 12? All right, so that's a kind of interesting permutation. I've written it, and it's what? This is the disjoint cycle factorization, right? I presented it in that way. And we can ask, what are the orbits, right? What are orbits? What are orbits of, of H? So let's see here. Let's calculate what would the orbit of 1 be. So that would be what? This is sigma, well not sigma, let's say it's beta times 1 such that what? Beta is where? An element of H, right? Which in this case is the cyclic subgroup generated by sigma. So what is that? I mean, beta is really just sigma or powers of sigma, right? Sigma or sigma squared or sigma cubed or sigma to the fourth. How far do I have to go before I run out of new sigmas? What's the order of H here? $12? I think I'll buy that. The least common multiple of 4, 3, and 2 is 12. Sure. So this is a group of order 12. I will agree. So what's the orbit of 1? Can you guys tell me? That should be a subset of these will be subsets of what? The numbers from 1 to 13, right? So which subset is this? What's the orbit of 1? What happens if you think about sigma or powers of sigma as they act on 1? Where do they move 1 to? If you think about it, they're just moving 1 to 1, 3, 5, or 7, right? There's no way 1 can ever get to 2, 4, 6, 9, 12, or any of the things which are not listed there, right? So the orbit of 1 is actually 1, 3, 5, and 7. So this is kind of neat. The orbit of a cycle, it looks like it's going to be a list of the numbers in each disjoint cycle, right? Like what's the orbit of 2? It's going to be 2, 4, and 6, yeah? What's the orbit of 9? Nine goes to 12, right? So work it out, you get 9 and 12. And then what are the other orbits here? Remember, everything in N13 is contained in some orbit. So what are we missing? We got 4 plus 3 is 7. How many total do I got there? 9, right? How many things are in N13? 13. So we're missing what? 4 things, right? What are the other 4 things? What am I missing? Looks like I'm missing 8, right? What else am I missing? Looks like I don't have 10 anywhere, right? What else am I missing? Oh, 11 and 13, yeah. And so all of these are fixed by this permutation and all powers of this permutation, right? Which means that where do they orbit to under this action? They just orbit to themselves, right? They are fixed. So the orbit is just the singleton containing 8, 10, 11, or 13, respectively. So I think that's an interesting, perhaps an interesting calculation. So that was actually what's behind example 3.7.2, 3.7.3, and the comment at the top of page 117. They're all basically studying this kind of action, right? Now, this is not this is one action of the permutation group we can look at. And I think that's already kind of interesting. The connection between cycle types and the orbits, I think, is neat. But what is deeper, though, is the discussion of the conjugacy action. All right, so let's define that. That one I have not yet introduced. Let me bring this over here, make sure I don't forget anything. And so this is my example 7.3.1, which probably should be a definition. And so here it is. If we have G a group, and we're taking the group to be the set on which we're going to act, and we'll define action of G on itself as follows. We'll say that G star X is equal to Gx G inverse. All right? Now, does this define, is this a group action? What do we need to check? What are the 3 axioms? Well, we'd like what? Well, we'd like the 3 axioms? Yeah. I guess there's a precursor to that, which is that the star is actually a map what? So there really is 3 things. The first thing that you sometimes forget about is that it has to take pairs from G cross S and map them to what again? S, right? But in this case, S is equal to G, and does the conjugation of a group element by a group element give you back a group element again? Yeah, it does. So at least that's well defined, yeah. Yeah, I know this particular red is worthless. Did I get it? No, not quite. Close enough, okay. So hit the trash can. All right, here, I will, oh, you have something against the flames. Okay. Oh, hey, she didn't back off of that. Bonus point. All right, no. I better not start giving bonus points for sports disparaging comments. Yeah. I better not start. It's a path I won't be able to get off of. Anyway, so this is at least making sense, given the definition right there, yeah? So that's a starting point. And then axiom 1, well, we're supposed to have that E times X is what? So you're looking at EX E inverse, also known as EXE, also known as X. So there you go, axiom 1, that one's good. Axiom 2, if we have, AB acting on X, what do we got? We've got AB, X, AB inverse. Did I talk about this last time? Not quite. I talked about the right group action versus the left group action, right? Which is kind of the same calculations, but this is, in some sense, putting them both together. Yeah? ABX, B inverse, A inverse by sock shoes, which of course is A times BX, B inverse, which is, by the way, A times B times X, which is the sort of modified associativity I need, the axiom 2 for the group action. Indeed, conjugacy is a group action of the group on itself. And the orbits of the conjugacy action are very interesting. What's the orbit? What's the orbit under conjugacy action? What's that look like? What's the orbit of X? It's G times X, right? Such that G is in G. That was our general definition of orbit, right? All things that are mapped to by a given point under the group action as we cycle through all possible group elements. But what is that? Here, that's what? By definition, this is what? Gx, G inverse, such that G is in G, right? So this is, the orbit is in fact the set of possible conjugates, right? This is the orbit under the conjugacy group action. And this is also known as the conjugacy class of X. There's a notation, this is also sometimes denoted X to the G. In this context, it's the conjugacy class of X. And we can do more. We can talk about the centralizer. What's the stabilizer of X, rather? I think I just ruined it. Sorry. Should have given you the spoiler alert there. What's G sub X? The stabilizer of X is what? This is going to be, how's it go? It's G and G, such that what? G times X equals to X again, right? So what does this condition here mean? G times X equals X again, the stabilizer condition. For the conjugacy action, that's G, X, G inverse equals to X, which is a hop, a skip, and, well, not even that, it's just a jump. It's Gx, that gives us Gx is equals to Xg, right? I think this one's dead. Oh. Hey, that one. I couldn't do that again if I tried. I think you should complain more forcefully about this marker, though, Morgan. This one's much worse than that red one I was using. Do you say you disagree? Because of the sports? Oh. like, I'm red-green colorblind. They're all the same. No. Okay, so anyway, the point is you should recognize this condition. This is the condition that X commutes with G, right? And so in other words, the centralizer under the conjugacy group action is nothing more than the centralizer of X. So the stabilizer is the centralizer in this context, all right? And finally, the fixed subset. So we had orbit, stabilizer, and then finally the fixed subset, which I always forget the notation for, which is S to the G. How did I define that? That was, what was it? It was G and G such that G and G such that XG, X inverse is equal to G again for all X and G. So what is that? Well, I mean, this, of course, is really the condition that xg equals to gx for all x and g. So we're talking about the set of group elements which commute with all other group elements. This is the center, yeah. All right. So the orbit, the stabilizer, and the fixed subset all have special and already known meanings to us as they relate to the conjugacy group action. Which means that if we think about the orbit stabilizer theorem, the counting that we learn there will impact these objects that we already learned about, namely the centralizer and the center, all right? That means we're going to get new counting theorems from applying the theorem we proved last time, the orbit stabilizer theorem, to this particular action, all right? So, let's see here. Now, before I do that, I'm just going to pause and take a second. Well, I'm actually going to, what I'm going to do is I'm going to focus our attention on the conjugacy group action as it works specifically on the group of permutations. So let's look at conjugacy for the, Sn. So it's interesting to understand the structure here in this particular case, right? So, and the interesting thing is you can start doing some calculations. If I let alpha, and I'm just going to do this so I don't have to think too much, but let alpha be the product of 1, 2, and 3, 4. So two cycles. 1, 2, and then 3, 4. All right? And then we can look at the conjugacy group action on this thing, see what happens. Like let's see what the orbit of alpha is as we cycle through different choices in S4. All right? So here's a few sample calculations. Let's actually conjugate in S4. Is my I'm about to do here. So if I do 1, 2, 3 alpha, and then 1, 2, 3 inverse, which would be what? That's 1, 2, 3, 1, 2, 3, 4, 3, 2, 1, yeah? What's that work out to? Let's calculate. So I put in 1, 1 goes to 3, 3 goes to 4, 4 goes nowhere. Apparently 1 goes to 4, right? Look at 4, where's 4 go? 4 goes to 3, 3 goes to 1 again. Oh, close the cycle. So 1, 4, and pick up at 2. 2 goes to 1, 1 goes nowhere, 1 goes to 2, 2 goes to 3. Look at, 3 goes to 2, 2 goes to 1, 1 goes to, oh, close the cycle. So there you go. When we conjugate alpha by the 1, 2, 3 cycle, we get back 1, 4, 2, 3. let's pick another one. How about, what if we did like 2, 3? Let's conjugate by 2, 3, alpha, 2, 3 inverse. What's 2, 3 inverse, by the way? Yeah, 2, 3. 2, 3 is its own inverse, right? Because it's order 2. So work this out. What do we get? Where does 1 go? 1 goes nowhere, 1 goes nowhere, 1 goes to 2, 2 goes to 3. So 1 goes to 3. And let's see here. Then 3. 3 goes to 2, 2 goes to 1. Oh, close the cycle. Look at 2. 2 goes to 3, 3 goes to 4. 4 goes nowhere, 2 goes to 4. And then you can check 4 goes to 3, and 3 goes back to 2. We close the cycle again. All right, can you guys think of anything else in S4 I should maybe try to conjugate by? What if I did, we could do 1, 2, 3, 4, right? Let's try that one. 1, 2, 3, 4 alpha, 1, 2, 3, 4 inverse, which would be what? Say again? 4, 3, 2, 1? Yeah. You know, you think about the trouble it was of finding inverses back in pre-calculus. Isn't it kind of embarrassing how easy it is to find the inverse of permutations when you write them in cycle notation? It's really kind of obnoxious, isn't it? I mean, it is. And so we calculate that, and what are we going to get? 1 goes to what? 1 goes to 4, 4 goes to 3, 3 goes to 4, and then 2 goes to 3. Okay, there we go. That's what's going to happen. So we get 1, 4, 2, 3. Now, the reason I knew that's what was going to happen is there starts to be a pattern here. When we conjugate a cycle, what happens to it? Here, let's try something else. What if I take the cycle, 1, 2, 3, 4, 5, right? And I conjugate by the cycle, I don't know, 6, 7, 8. So this is this is in a bigger, here in S8, another related but similar calculation. Let's try this out, see what happens. So I'm thinking of this as being my cycle alpha, so to speak, and here's my G, and here's my G inverse. Yeah, what happens? 1 goes to where? Oh, fine, let me rewrite that. 6, 7, 8. 1, 2, 3, 4, 5. 8, 7, 6, yeah? So 1 goes where? Nowhere. 1 goes to 2. Nowhere. Okay, 2 goes where? 2 goes to 3. And then 3 goes back to 1 again. Okay, great. Where's 4 go? Nowhere. 4 goes to 5. Okay, yeah, great. So this is not surprising because I conjugated by a cycle which doesn't move anything in alpha, right? So G and G inverse do nothing. They don't move anything. So they don't conjugate the cycle at all. I mean, they fix the cycle. But this serves to illustrate the larger point, which is when we conjugate a cycle in Sn, what's being preserved is actually what's called cycle type. So if I did this one, instead of, let me make it more interesting. If I was to do, 3, 8, 7, 1, 2, 3, 4, 5, 7, 8, 3, what would that work out to? 1 goes to where? 2. All right, 2 goes where? 2 goes to 3, 3 goes to 8, and 8 goes to 3, which goes to 1, so we close the cycle. And then what's next? Well, I don't know, 4 maybe? Where's 4 go? Nowhere. It goes to 5. 5 goes nowhere. And how about 5? 5 goes nowhere, 5 goes back to 4, 4 goes nowhere, like that. What about 7? What happens to 7? 7 goes to 8. 8 goes to 7 is fixed. Is there anything else at play here? The other numbers are clearly fixed, right? But this is actually my first, this is a better example, because you can see again that conjugation preserves what? taking a 3 cycle times a 2 cycle to another 3 cycle times 2 cycle. Not the same ones, right? But the larger point here, I'm trying to get you to make an observation. Here's the observation. Conjugation preserves cycle type. And so what that means then is if we look at the orbit of a given cycle in Sn, and as we orbit under the conjugation action, right, what are we going to do? We're going to trace out all possible cycle types of the given cycle type. So like if we're in, let's just say S3 to keep things a little bit simpler. If I was to look at the orbit under conjugation of, say, 1, 2, you know what I get? I would get 1, 2. I would get 1, 3. And I would get 2, 3. Because those are all the just plain old, what? 2 cycles. If I look at the orbit of 1, 2, 3, right? I get all 3 cycles, which are what? There's, how many of those are there? There's just 2 of them. What are the other possible? Was there anything else in S3? We have the identity, right? Which is just got, there's just one of them. This is not an action. These partition S3, right? 3 plus 2 plus 1, 6. That's the order of S3. In the notes, I share with you the breakdown for S4. Let me put that up, actually. You guys have a good break? Yeah. Oh, actually, before I even get to that example, a corollary. The number of permutations in Sn with a particular cycle type must divide n factorial. Why is that? Yeah. Okay. Okay. Well, here's the thing. This is the orbit, all right, of this is a cranky notation for the orbit of sigma under Sn, right? The conjugacy class. It's all possible conjugates of sigma under Sn's conjugacy action. And so what I'm saying is that's the number of permutations with the same cycle type as sigma. And I guess technically I haven't proved that, but I've given you some evidence to show you that that's what happened, yeah? So corollary 3.76 says that the order of the conjugacy class is equal to the index of the centralizer of sigma with respect to Sn. But we know that the order of the centralizer subgroup times the index of the centralizer subgroup of sigma is equal to the order of Sn, right? Which is n factorial. And so, what does that say? It says the number of, permutations of a particular cycle type, which is the size of the orbit, has to divide n factorial, which is the corollary. Now, this corollary 3.76, which is referred to, which one's that? let's take a tour back memory lane here. This is the orbit stabilizer theorem specialized to our current context, all right? And it says this: if G is a finite group and X is in G, the number of conjugates to X is the index of the centralizer, right? So, and again, that's just the, what was the orbit stabilizer theorem? It said what? How big is the orbit? It's the index of the stabilizer, right? But here the stabilizer was what? The centralizer of X. So, all right. So, this is interesting. The number of permutations of a given cycle type has to divide n factorial. That's kind of neat. And also the number of distinct cycle types, when we add the number of each different distinct cycle type up, since this different cycle types are forming orbits which partition the group of permutations, it must be that the sum of these different numbers of cycle types must add up to n factorial in total, right? So for S4, you have one identity cycle. You've got 6 2 cycles, right? Because you've got 1 2, 1 3, 1 4, 2 3, 2 4, and then 3 4. Those are the 6, yeah? And then for 3 cycles, you actually have 8 distinct 3 cycles you can count. You have, in fact, 6 distinct 4 cycles, and you have 3 distinct products of 2 cycles, like this. And so those are your cycle types. You've got 1, 2, 3, 4, 5 different cycle types. Each one of these numbers divides 4 factorial, which of course is 24. And they also sum to 24. So we've got this interplay between a partition and like an additive partition. The sum of these numbers is equal to 24, and each one of the numbers also dividing 24. It's interesting. Here is a hint for S5, which I don't think I assigned as a homework problem this year, so you're safely inoculated from this hint, I guess. But that's the number of identity. I think that's 1 cycle, that's 2 cycles, 3 cycles, 4 cycles, 5 cycles, and I forget what these are. All right, shut up about that. Anyway, my point is that the counting numbers of distinct cycle types gets fussier as n gets larger, right? It's essentially just a combinatorics problem, which means I'm bad at it. We all know that I don't know that 4 times 15 is 60, right? And 4 and 15 are relatively prime, so I put 42 as the largest order possible, and what was it? S5 cross S8. I mean, most of you already know that that's nonsense. No one emailed me. That's like the mathematical equivalent. It's like I'm walking around for weeks with like, lettuce between my front teeth, just having conversations with you guys, and nobody's like, hey, there's a little, come on, somebody say something. I mean, I'm glad you said something finally today, but actually that was only after I brought it up. You're bad friends. Bad friends, I say. Let me know about my errors. I like to know about my errors. Heavens knows I make them. All right, so now what's next here is to put these pieces together and to actually see, this is the sort of precursor to the CeLO-P theorems. It's part of a family of theorems about elements of order prime or elements of order prime squared, and there's some really neat, interesting theorems about such things that I might cover next semester in 422. I'll cover this one here because it's within our grasp. And the proof is important because it introduces you to a technique which we have maybe not done in here yet. So I think it's worthwhile, definitely worthwhile going through this proof. But this is the theorem. If G is a finite group with order divisible by a prime P, then G contains an element of order P. And the proof is actually going to use the orbit stabilizer theorem and the conjugacy group action. That's what it's going to do. There we go. All right, so assume you've got a finite group with order divisible by prime P. What we're going to do is we're going to do induction on the order of G. Now that's A little bit different than the induction proofs you saw in Math 200, right? Like, I don't know, to me that's kind of scary when I read a textbook and it says something like, we're going to do induction on the dimension, or in this case, the order of the group. And I was like, it gives me a sense of, I don't know, I feel ill at ease. And, but anyway, here it is. So if the order of the group is 1, then the theorem is trivially true because 1 has no prime divisors. Yay. All right, so suppose the theorem is true for groups up to order n minus 1. All right, and consider the order of the group being n. So we're using strong induction, right? We're assuming that the induction hypothesis is true, not just for all n up to the 1n we're looking at, all right? This is a strong induction proof. So if we have x's in G, then we can look at the order of x to the G, which was what? What was x to the G? This was the conjugacy class of x, right? Remember that the orbit is as big as the index of the stabilizer, which in this case is the centralizer of x. So the size of the conjugacy class is equal to the index of the centralizer, all right? Now, great. So if x is not in the center, what are the centralizers? I'm going to say this. Let's see here. What if x was in the center of G? What would the conjugacy class of x be? What happens if x is in the centralizer of G and you conjugate it by anything else in the group? If it's in the center of the group, it commutes with all the group elements, right? So under conjugation, something in the center just conjugates back to itself. So the conjugacy class of something in the center is very boring. It's just the set containing that one point you're conjugating. So we want to look at points that are not like that, right? If a point is not in the center, that means under conjugation, there may exist 2 points in the conjugacy class of x, right? It's not just x again, because there's something that doesn't commute with it, which means that conjugacy takes you someplace other than x. So if x is not in the centralizer of G, then x to the G has more than one element. Consequently, the centralizer, which by the way is a subgroup of the group, has order which is smaller than the group, which means this has order less than n, right? So we can apply the induction hypothesis to the centralizer of x. And so if P divides the order of the centralizer, right, for some x which is non-central, then by the inductive hypothesis, we know that Cx is a subgroup of G and it has an element of order P, right? Because if the prime that P divides an element, divides a group with order less than n, then by the induction hypothesis, there exists an element of order P. So what's the other case? It remains to study the case that so you guys really don't complain about that? Like, I feel like I talked about this before, but I'm disappointed Liberty students are not complaining about the projectors here. I think it's a problem. Because I talked about this in differential equations, and you guys looked at me like, what's the problem? Does it in all our classes. You just used to the floor 3 one?
They're really bad.
Oh, this is nothing compared to floor 3?
It's like elephants are walking on the fourth floor. You can
Yeah.
from the projectors.
Yeah, I don't know. I just, you know what we need? We need like, it would be very loud though. I was thinking like drones, like projector drones, you know? Could like, you know, but then it's like zzz, the whole class. That'd be annoying. You need like maglev, right? Something like that. I don't know. Hey, next time engineering comes to me asking for a semester project, I'm going to tell them I'd like you to stabilize their projectors in this building. That's going to be my, yeah. I usually tell them something like, give me a universal hack to security passages here, but they always reject that as being illegal. Apparently that's part of their project guidelines, is it has to be something legal. Fine. Anyway, it's no fun. No fun at all. Okay, so also P might, okay, we're good. Oh, yeah, we're good. So if P does not divide this, oh, come on, this doesn't even make sense. What do I mean here? The order. Thank you. Very good, Stephen. So that should be the order of the centralizer. If P does not divide the order of the centralizer for all non-central, I mean, if there's even one x for which this works, then great, we found an because if there's an element of order P in the centralizer, that means there's an element of order P in the group at large, right? So for this to fail, it has to fail for all x, right? So suppose P does not divide the order of the centralizer for all non-central x. And we're still assuming that P divides the order of G. And we still have that, what's this theorem here? Order of G is the index of the centralizer times the order of the centralizer. What's this theorem? What's that? Yeah, Lagrange. Or if you're from Georgia, Lagrange. Yes, very good. No, it's fine. I don't dispute it. It's a good place. Went to the Great Wolf Lodge there a few months ago. It's a good place. It's a good place. I digress. Now, so we have that P divides this, right? And this number is a product of these two numbers. Euclid's lemma says if you've got a prime divides that, then if we got a number is equal to A times B, and if the P divides the number, then either P divides A or P divides B, right? Primes in that sense are atomic. They can't be split. It's got to be in one or the other. Or it could be in both, right? Sure. But and the current consideration, it's that P does not divide this, right? So by process of elimination, P must divide that. So in this case, we have that P divides the order of G, the index of the centralizer of X. And since the conjugacy class is partition G, right, applying theorem 3.6.12 to the action. So this is the orbit stabilizer theorem, I believe. In the current context, the orbits, there's two different things, right? There's the singleton orbits, which are in the center of G, right? And then over here, these are the non-singleton orbits. These are the size of the orbit for the non-central X. It's the number of things it conjugates to. That's what this is. So this is saying that the order of G is, the number of things in each orbit added together. And it's broken down into the orbits that are just singletons and the orbits that are more than singletons, which again are described by the index of the centralizer of such elements. And the sum is taken over a set of non-central x's which are sufficient to cover all different partitions of the group into the conjugacy classes. Such x exist and can be found because we're talking about a finite group. So by exhaustion you can set up this sum. Does that make sense? What I'm saying? Hope. But the reason that this is true again is the orbit stabilizer theorem, because the sum of the sizes of the orbits has to be equal to the size of the group. Well, the size of the set, right? But here, the set on which the group is acting is the group itself, right? So this is, in the orbit stabilizer theorem, that would be the cardinality of S, right? The size of S, but in this case, it's just the size of G. But, and here I'm just saying what I just said again. So if you look at it, P divides G and P divides this, right, for each I, which means that P must divide the center of G. Let me just go back again. Poor planning on my part. So what we've just argued is that everything in this sum is divisible by P, right? Everything in this, well, this is divisible by P is assumption, right? So if we subtract that to the other side, we have that the order of the center of G is the difference of the order of G and the sum. Everything in there being divisible by P. That implies that the order of the center of G is divisible by P. All right? So then, no proof is complete without a gap. There's a theorem that you could prove separately, which is that if you have an abelian group whose order is divisible by P, you can prove that it contains an element of order P. So with that little theorem, again, this is a jump in my proof. With that little theorem in hand, then because Z of G is abelian and we have P divides the order of G, that implies that the center of G actually contains an element of order P. And again, we find that G contains an element of order P in all possible cases, and that's the theorem. And also, this is the so-called class equation. This class equation formed the heart of the theorem, which is a way of looking at the order of a group in terms of the order of the center and then the sizes of the distinct conjugacy classes in the group. This we can explicitly calculate for the permutation group because this is just the number of cycle types. Like the permutations are just different. You know, you've got what's in the center. What's the center of the permutation group? Which permutation commutes with all others? I hear some votes for the identity permutation. Great. Any others? No. I mean, the permutation group is kind of maximally non-abelian in some sense. I mean, it's very non-abelian. The center is pretty small. And so like for Sn, if we apply this class equation to the permutation group, it's just 1 plus, you know, the number of things in each cycle type. Because the number of permutations of the same cycle type are related by conjugation. Okay? Now that's for Sn. If we look at this class equation for a subgroup of Sn, it could be that the cycle types are spoiled. Like if you try to look at the class equation for An, there are going to be some cycle type, sets of cycle type, you know, set of permutations of a given cycle type, which could be split into two separate conjugacy classes. You could be missing an odd permutation you need to mix and match different parts of that conjugacy class, those conjugacy classes for a subgroup. I think that's one of your homework problems, is why I'm telling you about this. But any questions about all this? So previous years, past this, there's another 2 lectures on like P groups and silotheorems. And I just decided that stuff is a bit much for you guys. So I'm instead going to go a different direction and talk to you about matrix groups Wednesday and Friday. I think it's more appropriate to the level of this course, and I think it's geometrically interesting. And so I think it's going to be a better course for you guys because of this. Now, if you're interested in the silotheorems and that, I would say, intermediate group theory, come join us for Math 422. We'll do some of that in there because we need it to understand the larger question of Galois theory, in particular, solvable versus simple groups. Some of these, I would say, intermediate group theory theorems play an important role. Anyway, that's pretty much all I got to say about this material. Any questions? Let me skip back for a second. Bethany brought to my attention, I was happy, at the end, right here. So I still owe you guys about 10 minutes to jibber jabber about this stuff, right? I never did quite cover this. I hope you've read it and have thought about it and meditated upon it. One of the things that should have confronted you immediately in the process of this meditation is, what is this? Yeah. Great. I mean, this is kind of neat. I mean, there's an explicit formula to show you that we have a surjection. Great. But this is actually supposed to be isomorphic to the non-zero reals under multiplication. So there's a missing equals squiggle r upper x there, all right? That's what's missing. So we have a minute, literally a minute. What's a good test question about group actions, since you guys are interested in test questions? What would you say? There's different questions. I mean, one obvious question, here's a group action. Calculate the orbit. That's sometimes a pretty fun question. You've got some homework questions like that right now that you're working on, right? What's another one? Oh, how about this? I propose something's a group action, and you have to decide, for or against. Yay or nay, is this actually a group action, right? That's actually a pretty cut and dried problem, because what you have to do is check 3 things, right? That it's actually set up like it's supposed to, and that it satisfies axioms 1 and 2. That's not a bad question at all, really. Then there's other questions like calculate the stabilizer, right? I mean, any of these things we've defined, we could ask questions about. Exhibiting the class equation for a group isn't that bad, actually, because what that really just means that you have to do is to understand conjugacy classes for the group. Now, the one example where I think you should be fast at that is the permutation group, because I've given you a lot there. I've told you how conjugacy works out. For the permutation group, it's just cycle type. Now, other groups, who knows? We have no idea what the conjugacy classes look like for other groups. We just don't know, given our current work. Any other ideas? I mean, there are bits of the orbit stabilizer theorem proof that you probably should be able to reproduce, right? I think asking the whole proof is maybe a bit much, but certainly there's elements of it that make good test questions, right? Can you define the function which gave the bijection on which the counting is built, right? Knowing that would go a long way in understanding the proof. So anyway, I hope you guys had a good break. Oh, yeah, you can turn it off.